Let's take a look at some examples of vector spaces using the definition that we just gave. Here's an example. I'm going to let V be the set of all 2 by 4 matrices. I could have chosen any side, just for example, I'm choosing 2 by 4. And what I have to do is I've got to show you how to add and how to multiply by scalars, and then show that they satisfy the 10 axioms. So I just want to add 2 matrices together the way we have always added matrices together, add component-wise. So first component here, first component there, that one, that one. Just add the entries in their spots. And likewise, scalar multiplication is just the way we've always multiplied scalars times matrices. Now, in order to check to see if this is a vector space, I have to show, does this definition of addition and scalar multiplication for these objects satisfy the 10 conditions of a vector space? So I go back up here and I say, if I add 2 vectors, is the sum, so if I started with 2 matrices that were 2 by 4, did I end up with a matrix that's 2 by 4? Yes. Okay, so that one's satisfied. Is addition commutative? Well, I happen to know that addition of matrices is commutative, so yes. Is the addition associative? Well, we've already actually proved that earlier in the quarter, that addition of matrices is associative. Is there a zero object in V? Is there an object that when you add it to anything, you get that same thing back again? Well, I think you can see that if I take a 2 by 4 matrix that has all zeros in it, that would be my zero matrix. Do I have additive inverses? And the answer is yes. If you take any 2 by 4 matrix, so if I, where do I want to write this? So if I take, A, B, C, D, E, F, G, H, the minus of that, I think, would be minus A, minus B, minus C, minus D, minus E, minus F, minus G, minus H. That if you just take everything and change the sign of the entries, then when you add, if I add this matrix and that matrix together, I should get my identity matrix, which my identity matrix, or my additive identity, my zero matrix, would be, yeah, I add those two together, I get the zero matrix. So that's good. When I multiply by a scalar, do I end up with another object in, if I take the 2 by 4 matrix and multiply it by a scalar, do I get a 2 by 4 matrix? Yes, I do. These properties, does scalar multiplication distribute over addition? Well, we've proven this for matrices. This property satisfied that. All of these are satisfied. And yes, this is a vector space. It does satisfy that. Let's take another look. Look at another one. How about this one right here? This just has one thing in it. In fact, I should point out that vector spaces always have to have at least one thing, because that axiom, which one is it? Axiom 4 says there is an object, V. So you can't have an empty vector space. It has to have at least one thing in it. It has to have the 0 in it. In fact, if it only has the 0 in it, that's good enough. Because look at, if I define addition, I got one thing in it, it's called 0. And how do I add 0 plus 0? Well, it's going to be 0. And how do I multiply k times 0? Well, it's going to be 0. So now you go through and say, well, let's see. If I added 2 things in there, did I get something in there? Yes. Can I add these in either order? Yes. Is there an associative property? Is 0 plus 0 plus 0 equal to 0 plus 0 plus 0? Yes, it is. It's all equal to 0 on either side. Is there a 0 element? Yes, there's a 0 element. Are there additive identities for everything in there? Sorry, there are additive inverses? Yes, everything in here. Well, there's only one thing in there. It's its own additive inverse. If I multiply by a scalar, do I get something in there? Yes. Is there all those? I mean, you can go through and check that this satisfies all of them. And sure enough, it is a vector space. Here's another one. Functions. I want all the functions that are defined on the whole interval from minus infinity to infinity. And I got to show you how I add 2 functions. So if I have the function f and the function g, I'm going to make a new function out of them called f plus g. And in order to describe what a function is, I got to tell you what it does with the input. So f plus g of x is going to be, well, figure out what f of x is, figure out what g of x is, and add the two together. Right? For instance, if you wanted to look at sine plus cosine, and I say, well, what do you do? Well, that's going to be just figure out what the sine of x is and figure out what the cosine of x is and add them up, and that's going to be the result of sine plus cosine. Right? How do you multiply a constant times a vector? A constant times a function? Well, figure out what the function is and then multiply the result by the constant. This, it turns out, satisfies all the axioms. You might ask, what is the zero? Well, the zero function is the function that always gives, so the zero function is the one that always gives an output of 0. The graph, of course, looks like, you know, a horizontal line at 0. If you add that to any other function, you just get that other function back again. Here's an example. I want v to be the set of all integers, and I'm going to add integers the way I normally would add, and I'm going to multiply them by real numbers, scalars here, by just the same way I would normally multiply by real numbers. And now when I look at, actually I want to pull up the book here. And set this thing on the side there. Yeah, so when I look at, you know, if I add two integers, do I still get an integer? Sure. Is addition commutative? Yes. Is it associative? Yes. Is there a zero object? Yes. That would be 0. That's an integer. Are there additive inverses? Well, if you have 7 and -7, those are additive inverses, right? Sure, they're in there. If k is any scalar, so is scalar multiplication closed? Uh-oh. If I take an integer like 3 and I multiply it by any real number, do I get another integer? And the answer is no, because I can multiply 3 times a half and I get 1.5, which is not an element of V. So this is not a vector space. Not a vector space because it doesn't satisfy axiom 6. It actually, I think, probably satisfies every other axiom in there, but it doesn't satisfy axiom 6 because I can get outside of my set by just multiplying by real numbers, and I'm not supposed to be able to do that. So no, this is not a vector space. Here's another example that's not a vector space. Take the set of all pairs of numbers. So here's 2 pairs. I'm going to show you how to add. So I'm going to add this way. I'm going to just do your normal adding of pairs, just like in R2. But scalar multiplication is going to be a little bit different. Scalar multiplication, I'm going to multiply just the first one by k. So k times this thing is k times u1 comma 0. I'll just make that a 0. And it turns out that this satisfies, you can go through and check, it satisfies every single one of the axioms except 10. If I were to multiply 1 by the vector 3, 2, then according to this definition, it's 1 times 3, comma 0, which is 3, comma 0. Is that the same as the u that I started with? No, it's not. So 10 is not satisfied. Axiom 10 here is not satisfied. This is not a vector space. Okay. So there's a few examples. I'm going to do one in the next video, and I'll go through every single one of the 10 axioms to show how you would prove that something is a vector space. So here's some classic examples. Matrices, functions, the 0, this one right here, well, functions. This one right here is the single element vector space. That's a good example to keep in the back of your mind. It's a good, it's good to have in your repertoire. Anyway, we're going to look at one more in the next video.